So our first speaker today came with his comrade from Healthy Soils Australia. They came over the other day, and we're fortunate to have them staying at our house. So I've learned a great deal of extra information from Walter, and he's a wonderful guy. He is by training a microbiologist, and kind of a Renaissance man in terms of understanding a lot of related sciences and ways that we are able to restore hydrology. And the topic that we set before him is the natural history of the blue planet, which goes back a few billion years. And I think he can cover all the details in about 20 minutes. So please welcome Walter Jehne.
Okay, so look, yes, it's wonderful to be here, and thank you very much, and thank you very much for Brian and Susan for looking after us, and the very valuable discussions. And of course, let's hope this weekend we can continue that, not just talking here, but then in the workshops. Bit of background, Healthy Soils Australia, we're an NGO, but we're in a sense a network, and we connect to 500, 1,000 very, very leading, innovative farmers and activists in Australia in this whole business of land regeneration. We work with all levels, like most of it down grassroots innovative farmers, but also up in politics. Our ex-Governor General, that's like the Queen in Australia, when he retired, Major General Michael Jeffrey, he sort of said, look, there's one fundamental thing we must do globally for the future, and that's restore our landscape. And so in a sense, he invited us to come on board as a sort of scientific base. And so, yeah, we talk into politics at the very, very highest level. Of course, they always say yes, 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 but really that's not where the action is. The action is with the grassroots, with you, the people on the ground, because politics is necessary, but the real bottom line is what are the grassroots actions? What are we doing to deliver change where it's critically needed? And as far as critical need, of course, the real issue there is, in a sense, what are we doing in terms of this whole climate crisis, but not climate per se, but the impacts of climate in terms of water, food, habitat, and of course that translates to social stability. And it's really, that's a critical issue, because a crunch will come down that cascade: water, food, habitat, biosystems collapse, social collapse. It's happening now, different parts of the world, and really we've got 10 years, because if we don't, we're going to see, do we lose the means to do that? So it's quite a serious strategic issue, and the big news, the positive news is, of course, there are wonderful solutions. But just going into the climate story, just very rapidly, scaling down to sort of put it into context, obviously, yeah, the climate's been there for 4.6 billion years. And in a sense, we can look at it and what are the processes that are governing, and that's what's important. But in a sense, our recent climate debate started perhaps in 1958, 1962, and of course Charles Keeling in Hawaii then confirmed, yes, here is CO2 going up. But Charles Keeling also confirmed that it's not just CO2 going up, but you've seen the sawtooth graph. CO2 goes up dramatically every winter in the Northern Hemisphere as carbon dioxide is released, but every summer, every spring, it comes back down again as green plants draw in carbon and fix it as sugars and cellulose. And so the whole CO2 dynamic, the message that Charles Keeling gave us was the sawtooth, not just CO2 rising, the balance between emissions and drawdown, the balance between our use of carbon and the biosequestration of carbon by biosystems. And it's that balance that we've, in a sense, disturbed. And when we think of balances, that's something that we can address. So it's a question, how do we restore that balance? But then in 2005, we got another very serious awakening. Joachim Schellenhuber, big conference in Exeter in UK, and they more or less made the point that, look, things are happening now. Climate extremes, dangerous climate extremes were actually already occurring, and they would accelerate because there's a whole lot of positive feedbacks in the climate system. And these feedbacks were going to lead to things like, yes, more intense storms. And of course you've had them, Sandy and what have you. But in a lot of the world, systemic aridification. You know, how do we actually change rainfall patterns? We've had that since the mid-70s in our Western Australian regions, and you're experiencing that now in California. These are systemic, long-term aridification patterns, and yes, they are at a global scale, they are locked in. And of course, these are all hydrological, and that's the other big message from Keeling, but from the whole climate story. CO2 won't kill us. You know, submariners die when CO2 gets to 10,000 parts per million. But it's not CO2, but it's actually hydrology, you know, that gives life, but it's also hydrology that kills. And in a sense, these extremes, these positive feedbacks, are hydrological. So in a sense, that sort of changes the whole context a little bit. What is it that we can do to avoid these hydrological extremes? And in a sense, that's the paradigm shift that we here this weekend, but in the wider agenda, have to sort of say, look, can we address this problem as nature does on a much more holistic basis? The facts are very clear. We are not going to be able to change and solve this the climate problems through just emission reductions. The sad truth now is we're not even going to change it by just drawing down carbon, because the oceans, for example, they contain 38,000 billion tonnes of carbon. It's a massive buffer, and as we draw down carbon, the oceans re-equilibrate carbon back into the air. So it's going to take hundreds of years, and we don't have hundreds of years before these dangerous climate extremes impact. So the bottom line is we've got to find something much smarter. We've actually got to actively and safely and naturally cool the climate. And so we've got to change the narrative. We've got to change the debate, the whole inquiry of solutions into how do we actively, safely cool. And in a sense, that's our challenge here today. And it's really quite daunting in a way, but actually when we change the paradigm, it's also very empowering, because now we can go back to nature to say, well, look, how did nature cool the planet? How did it naturally regulate the climate? And of course, when we go back to climatology 101, and you know, a lot of us did that, and before the whole global warming debate, and of course we come to the reality, and it's still there today, that it's actually water. It's the dynamic process of water that governs 95% of the heat dynamics of this blue planet. Okay, and basically water's always been ignored in the recent climate debate because it was assumed that it was so dominant. Because it is so dominant, we humans could not have possibly influenced it to change the climate. So our human-induced climate change was always assumed to be due to CO2. But really, if we've got to cool the planet, we've got to ask the question, have we altered that hydrological heat dynamics? Can we use that to actually help us safely, naturally cool the climate? It's a relatively simple thing if we look at it at that global, bigger picture level. If we actually see that, we've got a sun, and that sun is constantly radiating incident solar radiation onto Earth. At the top of the troposphere, you know, the top of our dominant atmosphere, it's basically 342 watts per square metre of incident solar energy coming in. And our climate's been regulated by 342 watts of energy going back out. But because of our changes to the climate, we are now retaining an extra 3 watts per square metre in the Earth's atmosphere. And that's, in a sense, global warming. That's what we call the greenhouse effect. And so our challenge is how do we retransmit an additional 3 watts per square metre back out to space. That's less than 1% of that global heat dynamics. So the question in context is, look, it's a 1% systems change. And so while it's obviously at a bigger global scale now, it's a 1% rebalancing of heat dynamics. And can we, by managing the hydrology of the planet, do that safely and naturally? There's another very important thing here. This is a safely and naturally, because we've got another scenario coming on, and this is geoengineering. Because if we don't find a solution here, will we get into that Faustian trade-off to say, no, we have to artificially engineer the climate and start putting pollutants up there. And really, it's a very, very unknown, dangerous, risky consequence. And so can we, by all means, avoid that by doing it naturally? Okay, and so really what we're trying to talk about, what are the processes that govern the natural heat dynamics of this planet? You know, that 342 watts in and out. How have we changed those natural processes? And in a sense, what can we do to restore those processes? And in a sense, what we're saying here are the potential tools that we have in managing landscapes to do that restoration. Coming back to the punchlines right up front, the answer is yes, we can, right? Yes, we can, in a sense, cool this planet safely, naturally, that 3 watts per square metre. Yes, we can buffer the extremes that would the hydrological extremes that would otherwise create that crisis. Yes, we can draw down carbon through these processes to more than offset the 10 billion tonnes carbon net emissions we've got now. So in a sense, the headline statements I want to say is, yes, there are safe, natural ways. The only thing that's challenging is, can we do it in time? But that's why the urgency and that's why the empowerment of grassroots action in this is so important. Specifically for America, and I'm not here to tell you, of course, in America what has to or could be done, but you've got a fundamental challenge now. You see, you've lost the snowpack on the Sierra Nevadas. It's basically gone. I mean, it'll come back a little bit, but you're going to be threatened with that all the way. So can we find alternative, water capture, water harvesting options, rainfall harvesting options to replace that snowpack? Because 40% of your green food depends on that. Can we manage our forests so not like this year, that you can avoid those primary forests burning, degrading and being destroyed? So these are things, and the answer again is yes, we can, but what it means that we have to change the whole paradigms on which we're thinking and the tools that we're using, because we're not going to do it just by token marginal reductions in emissions. And it's those tools then that we want to talk about, right? What is it that we have to do? What is this range of what are actually 10 hydrological processes that nature uses and that we too can get into, right? And the first primary stepping stone, and it's again so simple, so elegant, and you'll see the logic as we go through these 10, and that's really, how do we restore the Earth's soil carbon sponge? Okay, because if we're talking about managing hydrology, the issue is how do we actually have the water that's available on the land to do these hydrological cooling processes. So the first step is, how do we rebuild the Earth's soil carbon sponge to provide the water for these cooling processes? The second step then is again very logical and simple, because if we've got water in the sponge, then we've got the potential for transpiration, for green plants to take that water and transpire it through their leaves and basically take that water back up into the upper atmosphere. And what is important that every gram of water that's transpired by those leaves takes up to 600 calories of heat energy from the surface back up into the upper atmosphere, from where it can get dissipated back out to space. So those trees are actually a powerful hydrological air conditioning system. And in a sense, Michael talks about this in the small water cycle, or that point of the latent heat fluxes of heat from the surface going back up into the atmosphere to cool that surface. And it's prodigious, because basically on average 24% of the incident solar radiation naturally gets transpired through these latent heat fluxes up into the upper atmosphere. And we have fundamentally changed that. We have fundamentally changed that process by degrading and deforestation vast areas, 75% of the Earth's forest, and we've created 5 billion hectares of man-made desert over the last 10,000 years. So we've fundamentally changed the surface. I'll go quickly through the other ones. There's a whole series, but actually I have a discussion paper that we can put on, the websites and stuff, where we go through each of these, the science behind each of these processes, and also on Sunday. So on Sunday, if people are interested, we can actually have a workshop and detailed questions and answers on all of them. Okay, so basically it's extending the longevity of green growth to keep this transpiration going, right? The other important thing is to extend plant covers so that we keep on protecting the soil surfaces, so we have an albedo reflectance of solar energy from the surfaces. And again, that can significantly cool those surfaces and reflect heat back to space. The next one that's very critical, which we've changed, is actually avoiding the exposure of surfaces and avoiding the erosion of dust, because these dusts actually are very fundamental in the atmosphere. They create hazers, water hazers in the air, and these water hazers in the air are very significant absorbing heat. And we've got a phenomenal global dimming, whereby basically 20% of the incident solar radiation is now being absorbed by these hazers in the atmosphere. So the length of time those hazers in the atmosphere are critically important. We've also then got to sort of basically stop the heating of the Earth's surface. And this is actually pretty fundamental. Every bit of solar energy that hits the soil gets absorbed by the soil, and of course raises the temperature of the soil. But like any black body radiator, that soil will then re-radiate that energy back out to space as infrared long-wave radiation. That's the sensible heat that Michael talked about yesterday. But that infrared radiation is much more important, because that's the primary variable and primary factor driving the greenhouse effect. And you've always heard of the greenhouse effect as, it's the number of CO2 molecules in the atmosphere that are absorbing this re-radiation. And we've seen that as the only variable that we can control. But in fact, there's 3 variables we control. We control how much re-radiation comes from the Earth, how much water vapor molecules are in the air, because that's a dominant greenhouse gas, and how much CO2. And what we're really saying, by keeping the Earth's soils cooler, we can fundamentally turn down the greenhouse effect. We can fundamentally turn down the amount of re-radiation of energy back up into space. And that's governed by physics, the Stefan-Boltzmann equation. I mean, you don't all have to know it, but it's a simple matter. The amount of re-radiation is a constant times the 4th power of the temperature. That's the quantity of re-radiation. So if we have a cooler surface that's protected and moist, stays below 20 degrees in most environments, that's a fundamentally different environment than bare exposed soils that heat up to 60 degrees, because the amount of re-radiation is governed by the 4th power of that temperature difference. So that's how we can turn down the thing. We then, of course, have a whole other series. We've got these hazers up in the atmosphere. So the question is, how do we get rid of those hazers because they're warming the atmosphere? And this is pretty important because there's another process where these hazers are nucleated to form dense, high albedo cooling clouds. Half the planet is on average covered by dense clouds. These clouds on average reflect 120 watts per square metre. That's about a third of the incident solar radiation back out to space naturally. So we've got this massive reflective capacity. So how do we enhance those dense high albedo clouds formation? Thank you very much. 1 minute. So again, critically important, and yes, we can. The actual coalescence of these hazers actually is driven by a series of precipitation nuclei, ice crystals, salts, and bacteria from biosystems. And these are hygroscopically coalescing these microdroplets to form the dense high albedo clouds. And so we can actually induce and reinduce that and reinduce significant cooling. And that's how nature did it. Those precipitation nuclei, of course, also very important because as they coalesce these hazers, they create rain. And so it's not just cooling, but it's restoring the rain. And that rain, of course, is recharging our soil carbon sponges, which we started with. And so there we are. We're building the hydrological cycle, okay, through transpiration, hazers, high albedo clouds, and then we're going back to rain. And so we're restoring that hydrology. There's several other processes involved, but we're running very short of time. So I think I just sort of, and we can pick up on these in the discussion paper and the workshop. But the point being is that, look, here is how nature naturally and safely cooled the planet. These are all practical tools that we directly can influence depending on how we manage our landscapes. And so I think it's really a very empowering opportunity now to say, how do we, through our land management, our farming practice, urban agriculture, restoration ecology, how do we look at rebuilding hydrology in the landscape, not just to provide us with the water we need, the food we need, the habitat, and the social stability, but also to cool the climate. Okay, thank you very much.